Module 2, Lecture A, Importing Data. By the end of this lecture, you will be able to load tabular data from CSV, Excel, and Parquet files into Pandas 2.3.1 DataFrames using appropriate read_ functions. Configure import options such as separators, headers, dtypes, and date parsing to correctly interpret raw files. And diagnose and fix common import issues, including bad encodings, unexpected missing values, and mixed type columns. Reading CSV files. Core Read CSV options. When you import tabular data from a CSV file, you are turning plain text arranged in rows and columns into a data frame. You first tell the data library where the file is located, such as on your computer, a network, or online, by providing its path or web address. The library then reads each line, splits it into separate fields, and organizes them into a grid of data. It usually assumes comma-separated values, a header row with column names, and automatically guesses basic data types. For clean, well-structured datasets, these default settings typically produce a ready-to-use data frame with meaningful labels and appropriate types. When importing real-world data, it is important to control how headers and rows are handled so the data frame reflects the true structure of the dataset. You can choose to treat the first line as the header, pick a different line if the file starts with metadata, or let the library create generic column names when no header exists. This flexibility is especially useful for files from older systems or those that include extra notes. You can also limit how many rows are read and skip certain rows so the imported data matches the logical content of the dataset rather than its original formatting. When importing CSV data, it is important to control how each column is interpreted so your data frame is accurate and useful. You can rely on automatic type detection or explicitly set types for key fields, such as keeping identifiers as text to preserve leading zeros, which is especially important in areas like finance or healthcare. You can also specify which strings should count as missing values, how many rows to scan when inferring types, and how to handle very large numbers or precise decimals. By choosing these options carefully, you create a clean, well-structured data frame that is ready for reliable analysis. Python code. Core Read CSV options. This material introduces how to use the Pandas Read CSV function with simple in-memory CSV text, focusing on a few core options. It explains how to control whether the first row is treated as a header, how to skip unwanted rows when loading the data, and how to specify the data types for selected columns. The goal is to give beginners, especially those working in Google Colab, a clear and minimal demonstration of these key settings without producing a lot of printed output. We start by importing the Pandas library, which is a key tool for working with and analyzing data. We also import the string.io class from Python's input-output module. This class lets us treat a string as if it were a file, so we can perform file-style operations directly in memory without creating an actual file on disk. Together, these imports make it easier to handle data efficiently in a flexible way. We create a multi-line text block that imitates a CSV file. The first two lines are just descriptive notes and are not part of the data. The third line defines the column headers for ID, name, zip code, and age. Every line after that is a data record for one person listing their ID, name, zip code, and age. This approach lets us work with CSV-style data in memory without needing a real file on disk. We create a buffer from the CSV text using a tool that lets us treat the string as if it were a file. This makes it compatible with functions that expect file-like input, such as the readCSV function in Pandas. Using this approach is especially helpful for testing or when handling CSV data that is generated or modified directly in memory without needing to save it as a physical file. The code first prints a message saying it will show a preview of the original CSV text. It then splits the CSV content into separate lines and selects only the first few. These lines are joined back together with new line characters and displayed. This quick preview shows the initial part of the CSV file, including any notes or headers, to give an overview of the data structure before further processing. The code moves the CSV buffer back to the beginning so that reading can start from the first byte again. As you read from the buffer, its position advances, so resetting it is necessary before any new read. This is especially important when you want to run multiple operations on the same CSV data, such as loading it into different data structures or configurations. Resetting ensures each operation sees the full original data from the start. We use Pandas to read CSV data from an in-memory buffer and create a data frame. By setting the header parameter to 2, we tell Pandas to skip the first 2 lines, which contain notes, and treat the third line as the header. This means the column names in the data frame come from the third line of the CSV. As a result, we get a clean data frame with meaningful column names that is easier to work with for data analysis. We begin by printing a short message to signal that we are about to show the data frame with its inferred data types, which helps set the context for the output. Then we call the head method on the basic data frame to display the first few rows. This quick preview lets us confirm that the CSV file was loaded correctly and see how Pandas has automatically assigned data types to each column. The code moves the CSV buffer back to the beginning so that reading can start from the first character again. As you read from the buffer, its position advances, so resetting it is necessary before any new read operation. This allows you to read the same CSV data multiple times without having to reload it. In short, resetting the buffer ensures every new read begins at the very start of the CSV text. We load CSV data into a Pandas data frame from memory and tell Pandas that the third line contains the column names, so it uses that line as the header. We also specify that certain columns, such as ID and zip code, should be treated as strings. This forces Pandas to interpret those values as text rather than numbers. Doing this helps preserve details like leading zeros and keeps the data handling consistent. The code first prints a short message to indicate that a data frame with controlled data types is about to be shown. It then displays the data type of each column, which were set explicitly when the CSV file was read. This check confirms that the ID and zip code columns are treated as strings. As a result, you can be confident that these fields are handled correctly according to the specified data types. This script shows how to read a CSV file with Pandas while controlling which lines are used and how column types are set. It first creates a CSV-style text that includes some non-data lines at the top, then reads it while skipping those lines, so Pandas can correctly detect the header and infer data types. Next, it reads the same CSV again, but this time forces the identifier and zip code columns to be treated as strings. The output highlights how specifying column types during import helps maintain data integrity, especially for values that should not be interpreted as numbers. Handling delimiters and headers. When working with CSV files, first check what character is actually used to separate values, because some files use semicolons or tabs instead of commas, which can cause all data to appear in a single column if you assume the wrong delimiter. Also verify whether the first row contains column names or is just data, since this changes how you should load and interpret the file. Paying attention to the delimiter and header row ensures that columns are labeled correctly and data fields are properly separated for analysis. Headers are important because they determine how you will refer to each column in your analysis. When a file has a clear header row, those labels become your column names and make the work easier. In practice, though, files may have messy headers, such as multiple lines or strange characters, so you may need to skip some rows, pick the correct header row, or replace it with your own labels. Being deliberate about how you handle headers helps you avoid confusion, like accidentally using the wrong column when names are duplicated or do not match the data. When working with CSV files, delimiters and headers can affect data integrity in subtle ways. If text fields or headers contain the delimiter, such as a comma, they must be properly enclosed in quotes. If this quoting is inconsistent, the parser may treat embedded delimiters as real separators, causing columns to shift and fields to mismatch. To maintain a correct table structure, always verify that every row, including the header row, uses delimiters consistently, and that any delimiters inside text are correctly quoted. Python code. Handling delimiters and headers. This section explains how to read CSV files that use different delimiters and header settings. It shows that if you assume the wrong delimiter, all the data can be merged into one very wide column instead of being split correctly. It also demonstrates how changing header options affects the column names and how initial descriptive rows can be skipped so they are not treated as data. Overall, the focus is on correctly configuring delimiter and header settings to load CSV data in a usable form. We start by importing Pandas, a powerful tool for working with data, especially when handling CSV files. We also import the string IO class from the input-output module. String IO lets us treat a string as if it were a file, so we can read from it and process it like real file data. This is useful for testing and demonstrations because it allows us to work entirely in memory without creating actual files on disk. We begin with a text string that holds CSV-style data, where each column is separated by a semicolon. The string contains headers for name, age, and city, followed by 2 data rows for Alice and Bob. We then print the first line of this string to preview the headers. This quick preview shows the structure and formatting of the data before we perform any further operations on it. We create a buffer from a string of semicolon-separated values using a tool that mimics a file. Then try to load it into a Pandas data frame while incorrectly specifying a comma as the delimiter. Because there are no commas in the data, Pandas treats the entire line as one long field instead of splitting it into multiple columns. When we display the first few rows, we see that all the values are collapsed into a single wide column. This demonstrates how using the wrong delimiter prevents Pandas from correctly parsing and separating the data. To work with semicolon-separated CSV text, we first place the text into an in-memory buffer, so it behaves like a file. We then load this buffer into a Pandas data frame using the read CSV function, telling it to use the semicolon as the separator, so the columns are split correctly. After that, we display the first few rows of the data frame to confirm that the data is properly aligned into the expected columns. We define a block of text that represents a messy file header, where the first two lines are just descriptions. The third line contains the real column names, and the remaining lines hold the data. We then display a message that we will show the first three lines, and loop through those lines by splitting the text at each new line. Printing these lines illustrates how the top part of a CSV file can include non-data information. That must be identified and handled correctly before loading the actual data into a data frame. We handle the messy header text by first turning the string into a file-like buffer using a string input tool, which lets Pandas read it as if it were a regular file. Then, we load this buffer into a data frame with the read text function from Pandas, telling it to skip the first two rows because they only contain descriptive information, not actual data. This makes the third line become the header row and defines the column names for the data frame. Finally, we look at the first few rows of the data frame to confirm that the headers were interpreted correctly. We begin by turning the messy header text into a string input buffer using a tool that lets us treat the string like a file, so Pandas can read it. We then define custom column names for product name, units sold, and revenue in US dollars to replace any default headers. Using the read CSV function from Pandas, we load the data from the buffer, skip the first three irrelevant lines, and specify that the data has no existing header. We pass in our custom names so they become the data frame's column headers, and finally check the first few rows to confirm that these headers were applied correctly. This material explains how to handle CSV files with unusual delimiters and headers using Pandas. It shows that if you read a file that uses semicolons with a comma delimiter, all the data ends up in one column, so you must match the delimiter to correctly separate fields like name, age, and city. It then demonstrates how to deal with messy headers by skipping initial descriptive lines so that the real header line becomes the column names, such as product, units, and revenue. Finally, it shows that you can skip more lines and manually assign your own column names, like product name, units sold, and revenue in US dollars to clean up non-standard CSV formats. Efficient large CSV loading. When working with very large CSV files, the main challenge is that they may not fit into memory all at once. Instead of loading the entire file, you can treat it as a stream of rows and process it in smaller chunks. With tools like Pandas, you read a portion of the file, apply operations such as filtering or aggregation to that chunk. Then discard it or save the cleaned results to a new data structure or a more efficient format like Parquet. This chunk-based approach makes it possible to handle large datasets that would otherwise be too big to process in one step, which is especially important in data-heavy areas such as web analytics and finance. When loading large files, focus on reading only the columns you actually need to save memory and speed up parsing. If you already know which columns are integers, categories, or other types, specify these data types instead of letting the software guess. This avoids expensive type detection, keeps types consistent across chunks, and makes the data more compact. As a result, operations like grouping and analysis run more efficiently, especially when you only work with key identifiers and metrics. When working with large CSV files, focus on fast, simple loading and postpone complex cleaning steps. For instance, you can read date columns as plain text first and convert them later. Avoid repeatedly merging many small data tables and instead collect results and merge once, or write directly to a compact format. Many teams use a two-stage workflow, streaming raw data into a columnar format and then performing detailed analysis on that optimized representation to improve both speed and resource usage. Python code. Efficient, large CSV loading. This lesson focuses on efficiently working with very large CSV files by reading them in manageable chunks instead of loading everything into memory at once. You will see how to select only the columns you actually need and how to explicitly set data types so the data is stored and processed more efficiently. Finally, you will learn to summarize or aggregate the information across all chunks while keeping memory usage comfortably low throughout the process. We begin by importing two key Python libraries, Pandas and NumPy, to prepare for data analysis. Pandas helps us work with tabular data using structures like DataFrames, making it easier to organize and manipulate datasets. NumPy supports efficient numerical computing with large, multi-dimensional arrays and matrices, along with many useful mathematical functions. Together, these libraries provide the foundation for fast and effective data processing in the code that follows. To create a sample CSV file that represents a large dataset, we choose to generate 50,000 rows of data. This provides a substantial amount of information that behaves like a real large dataset. Using this large sample allows us to later test how efficiently our CSV processing methods handle significant volumes of data. We begin by setting the random seed to 0 using the random tools from the numerical library so that the sequence of random numbers is always the same each time the code runs. This makes the results reproducible and easier to debug or compare. We then create an array of random integers to serve as customer IDs with values between 10,000 and 20,000. The number of IDs generated is controlled by the chosen number of rows, simulating a large set of unique customer identifiers. We use a random integer function from NumPy to simulate customer sign-up dates. First, we generate random days of the month, choosing integers from 1 to 27. Then, we generate random months of the year, choosing integers from 1 to 11. These two sets of random values represent the day and month when each customer signed up. Later, we combine them to form complete sign updates for all customers. We build a list of sign updates by combining each month and day from two arrays into a single date string. Each date uses the year 2024, followed by the month and day written as 2 digits with leading zeros when needed. A list comprehension handles this process by efficiently looping through the paired month and day values and generating the formatted date strings in one concise step. This code uses the random choice function from the NumPy library to create an array of country codes. It randomly selects from 4 options: US, CA, UK, and MX. The array is sized to match the dataset, which has 50,000 rows. As a result, each entry in the dataset is assigned a random country from these 4 choices, simulating country information for each record. This step creates random spending amounts for each customer using a gamma distribution with a shape of 2 and a scale of 50, which together control how skewed and spread out the spending values are. The number of generated values matches the number of customers, so each one receives a single spend amount. This method produces varied but realistic spending data that can be used for further analysis. We create a Pandas data frame called full DataFrame using a dictionary where each key becomes a column. The customer identifier column is filled from the customer identifiers array. The sign-up date column uses the sign-up dates list, and the country column uses the countries array. The spending in dollars column is filled from the spend dollars array. This organizes all the information into a clear tabular structure that is easy to work with and analyze. The code specifies a file name where the data will be saved as a comma-separated values file. It then exports the data table to this file. By turning off the option to include row indices, the saved file contains only the actual data columns, which keeps the output cleaner and easier to use. We begin by choosing only the specific columns we need from the CSV file, such as customer ID, country, and spending in US dollars. Focusing on just these columns means we do not load extra irrelevant data. This helps reduce memory usage and speeds up processing, which is especially important when working with large datasets. We create a mapping of data types to control how columns are read from a CSV file. The customer identifier column is stored as a 32-bit integer to keep it efficient for storage and processing. The country column is stored as a category type, which is ideal when there are only a limited number of distinct values and helps reduce memory use. The spending column in US dollars is stored as a 32-bit floating point number to balance precision and memory efficiency. By setting these types explicitly, we avoid automatic type guessing and make data loading faster and more memory efficient. The chunk size is set to 10,000, meaning the CSV file is read in blocks of 10,000 rows at a time. Processing the data in these smaller segments prevents the entire file from being loaded into memory at once. This approach helps manage memory more efficiently and is especially useful when working with very large datasets. We use Pandas to read a large CSV file in chunks so we can manage memory efficiently. We select only the needed columns, such as customer ID, country, and spend in US dollars, and we explicitly set their data types to avoid the extra work of automatic type detection. We choose a chunk size of 10,000 rows so each portion of data is manageable. This setup lets us iterate over the file chunk by chunk, making it easier to perform efficient computation and aggregation on large datasets. We begin by setting up an empty dictionary that will store total spending for each country. This gives us a clean starting point with no pre-existing values. As we process the data in chunks, we will use this dictionary to add and update the spending amounts for each country. Over time, it will accumulate the complete total spend for every country in the dataset. We process the CSV file in chunks, and for each chunk, we group the rows by country and compute the total spend in US dollars for each country in that piece of data. These per-country totals from the current chunk are then used to update a running dictionary of overall spending. For every country, we add the chunk's amount to its existing total, so the values accumulate across all chunks. This chunk-based approach lets us handle very large datasets efficiently while keeping memory usage low. This line of code prints a short message to introduce the results, explaining that the total spending by country will be shown using the chunked loading approach. It acts as a header for the output that follows. After this message, the program lists the total spending amounts for each country, calculated from the CSV data. The code goes through each entry in a dictionary that stores total spending by country and, for every country, prints a summary line. This line shows the country code and its total spending. The spending amount is formatted as a dollar value with commas for thousands and 2 decimal places for cents. This creates a clear, readable summary of how much each country spent. This script shows how to efficiently work with large CSV files in Python using Pandas and chunking. It first creates a large synthetic customer dataset and saves it as a CSV file. Instead of loading the entire file into memory, it reads the data in smaller chunks, selects only the needed columns, and sets data types to reduce memory use. For each chunk, it groups the data by country, sums the spending amounts, and accumulates these partial results. In the end, it prints the total spending for each country, demonstrating a practical way to summarize large datasets without overwhelming memory. Excel and Parquet imports. Selecting Excel sheets. When importing data from an Excel workbook, you should deliberately choose which sheet or sheets to load, because each one can have a different layout and data quality. Relying on the first sheet by default can pull in the wrong information, such as a summary view or a scratchpad, instead of the real dataset. By carefully selecting the correct sheet, you ensure that your data frame accurately reflects the data you actually want to analyze. When importing data from an Excel workbook, you need to know how sheets are identified and choose the correct one. Sheets can be referenced by their position, such as first or second, or by their names, like survey responses. In stable situations, sheet names may stay the same, so using the name works well. In more dynamic environments, names and order can change, so relying on a fixed position is risky. The safest approach is to inspect the workbook, find the sheet with clean data, and explicitly specify that sheet during import. When working with Excel files that have multiple sheets, you often need to decide which sheets to load and how to combine them into a single, consistent data frame. You might import separate sheets for different regions and then merge them, making sure the column names and data types match. In other cases, such as public health data, you may join sheets on a shared identifier, like linking patient demographics with lab results. Some sheets may hold metadata, such as data dictionaries, which guide your analysis, but should not be treated as regular data. Careful selection and handling of sheets helps ensure your data frames are accurate and ready for further analysis. Python code. Selecting Excel sheets. This lesson shows how to choose specific Excel sheets when importing data with Pandas. You first create a sample Excel file that contains several related sheets. Then you load particular sheets by referring to them either by their sheet names or by their index positions. Finally, you display and combine the imported data, so you can work with results from multiple sheets together. We start by importing the Pandas library to work with and analyze data organized in tables. We also import the Bytes.io tool from the Input-Output module. Bytes.io lets us create an in-memory buffer that behaves like a file, so we can handle Excel data directly in memory instead of saving it to disk. This setup is useful for efficient and flexible data processing. We start by creating a data fragment for United States sales data, listing cities such as Boston and Dallas with their sales in dollars. Then, we create a similar data fragment for Canada, with cities like Toronto and Calgary and their sales figures. Finally, we build a third data fragment for notes that contains a single internal summary entry. Together, these data fragments act as separate sheets in an Excel workbook, allowing us to simulate a multi-sheet Excel file for later analysis and operations. We first create an in-memory buffer so we can build an Excel file without writing it to disk. Using this buffer with a Pandas Excel writer configured with the XLSX Writer engine, we set up an environment that can hold multiple sheets. Inside this context, we write the USA sales data to a sheet named USA Sales and the Canada sales data to a sheet named Canada Sales, both without including the index. We also write the notes data to a sheet named Notes, again, excluding the index. The result is a single Excel file stored entirely in memory, containing 3 clearly labeled sheets for later use. The code first resets the position of the in-memory Excel buffer, so reading starts from the beginning of the file. It then uses a Pandas function to load the entire Excel workbook into a dictionary of data tables, with each table corresponding to a sheet. By requesting all sheets at once, it captures every worksheet in the file. Finally, it prints the names of all these sheets to give a quick overview of the available data. The code first moves the in-memory Excel file back to the beginning, so reading starts from the start of the file. It then uses a data analysis library to load only the sheet named USA Sales into a data table. Finally, it prints a quick preview of this table so you can see the contents of the USA Sales sheet. We start by resetting the in-memory Excel buffer to the beginning, so the data is read from the start of the file. Using Pandas, we then load only the sheets named USA Sales and Canada Sales, which gives us a dictionary mapping each sheet name to its data frame. Next, we concatenate these data frames into one combined data frame, telling Pandas to ignore the original row indexes so the result forms a continuous dataset. Finally, we print this merged data frame to display the unified sales data from both sheets. This script shows how to work with Excel files that have multiple sheets using Pandas. It creates an in-memory workbook with 3 sheets for USA Sales, Canada Sales, and Notes, each holding a small dataset. The script then reads the workbook to list all sheet names, loads the USA Sales sheet by name to preview its contents, and finally selects both the USA and Canada Sales sheets, combines their data, and outputs the merged result. This demonstrates an efficient way to manage and analyze data spread across several Excel sheets. Parsing dates and numbers. When importing spreadsheets into a data frame, it is important to control how dates and numbers are interpreted. Excel files often mix true date cells, text that looks like dates, and numeric codes used as dates, so the software needs clear instructions to turn them into meaningful values. If you rely on default settings, you may get a confusing mix of date-time objects, plain text, and unexplained integers that makes analysis harder. By carefully guiding how the data is parsed, you help ensure that time series plots, monthly summaries, and calculations like revenue totals correctly reflect the real-world information instead of quirks of the file format. When importing Excel data into a data frame, the same visual format can hide very different underlying values, especially for dates and numbers. A date that looks identical across files might be stored as a real date in one case, plain text in another, or even represent a different calendar date, depending on regional settings. Likewise, numbers that use commas and periods can mean different things in different locales and may mix percentages, currency, and regular numeric values. To avoid serious mistakes, especially in financial calculations, you must explicitly choose which columns should be parsed as dates, which should stay as text, and how to handle regional number and decimal separators. When working with columns that mix dates, numbers, and invalid entries, you need to decide in advance how Pandas should interpret them. Date columns may contain placeholders like TBD or comments, and numeric columns may include stray text, all of which should be treated as missing values rather than real data. By reviewing the raw Excel file and choosing which columns should be parsed as dates or numbers, you can configure the import process so that your data frame is clean, consistent, and ready for accurate analysis. Python code, parsing dates and numbers. This lesson focuses on how to correctly parse Excel dates and numbers when loading data with the Pandas read Excel function. It first shows the kinds of errors and misinterpretations that can occur when you rely on the default parsing behavior for dates. It then demonstrates how to fix these issues by using the date parsing options to explicitly control how date columns are interpreted. Finally, it highlights how to handle numeric values that use thousands separators or non-standard decimal characters so that they are read in as proper numeric data rather than text. We start by importing Pandas to work with and analyze data organized in tables. We also import the Bytes.io tool from the input-output module to create an in-memory buffer. This buffer lets us handle data as if it were in a file, without actually writing anything to disk. Together, these imports give us what we need to read and manipulate Excel data directly in memory. We begin by creating a dictionary called Data to hold sample information for a future data frame. It has 3 entries that act like columns: order dates, delivery dates, and budget text. The order dates are strings in different date formats to mimic inconsistent real-world data. The delivery dates are also strings, but one value is a placeholder that stands for a missing or unknown date. The budget text values are strings that look like monetary amounts, using commas for thousands and periods for decimals. This setup lets us show how Pandas can handle mixed data types and formats when processing tabular data. We start by creating a data table from a dictionary that includes dates and numbers in different formats. This table is then written into an Excel file format held entirely in memory using a byte buffer. The Excel writing method sends the table into this buffer and is configured so that row indexes are not included in the file. This approach lets us work with the data as if it were in an actual Excel file, without saving anything to disk, which makes testing and manipulation easier. The code moves the buffer's position back to the beginning so the data can be read again correctly. When the Excel reading function from Pandas reads from the buffer, it advances an internal pointer. Resetting this position ensures that any later read starts from the very start of the data, rather than from where the previous read left off. We begin by loading the Excel file with the standard Pandas function for reading Excel data, using its default options so we can see how it automatically assigns data types to each column. After the file is read, we display the data types of all columns to observe how Pandas interprets the contents. This step is important because it helps us detect any problems with automatic type inference, especially when columns contain mixed kinds of values such as dates and numbers. The code moves the buffer's position back to the start because reading the Excel file earlier advanced its internal pointer. By seeking to the beginning again, it makes sure that the next read operation starts from the very first byte. This allows the data to be read correctly a second time without missing anything. We read the Excel file again and explicitly tell the program to treat the order date and delivery date columns as dates instead of plain text. We also specify that the day first option is false, meaning the dates follow the month, day, year format commonly used in the United States. After loading the file, we check the data types of the columns to confirm that the date fields were parsed correctly. This verification ensures the dates are in the proper format for later manipulation and analysis. To convert the budget text column into numeric values, we first remove commas that act as thousands separators, so the text is ready for numeric conversion. We then use a numeric conversion function from Pandas, telling it to turn any problematic entries into missing values instead of raising errors. After this conversion, we compare the original budget text with the new numeric budget column to confirm that the values were correctly transformed. This script shows how to correctly handle dates and numbers when reading Excel files with Pandas. It starts with data that has inconsistent date formats and numeric values stored as text with commas, then writes and reads this data from an in-memory Excel file. Using the default read settings, Pandas may misinterpret these dates and numbers. By explicitly marking the date columns, the script converts order and delivery dates into proper date-time objects, and by removing commas from the budget values, it converts them into true numeric data. The results before and after parsing illustrate why it is important to specify parsing options to ensure accurate data types and values. Parquet data imports. When working with large datasets, you will often see them stored in Parquet format rather than as plain text. Parquet is a column-based, binary format designed for fast processing and good compression, and it works smoothly with big data tools such as Spark. Unlike text files, Parquet files include metadata that describes the columns and their data types, which makes loading them into a data frame more straightforward. Your main task is to review and, if needed, adjust this schema so the resulting data frame is correctly structured for analysis. When importing Parquet files, you must choose settings that ensure the data is interpreted correctly. Pay special attention to date and time columns so they load as either time zone aware or naive in a way that matches your analysis needs, and preserve types so you can convert time zones explicitly when required. Also, verify that numeric columns, especially in financial data, are imported with enough precision to avoid rounding problems. Overall, treat the import step as a schema negotiation where you align the stored metadata with the requirements of your analysis. When importing Parquet files from different systems, you need to control how categorical and string data are interpreted. Some files may use dictionary encoding for text, which matches categorical types, while others store the same fields as plain strings. It is important to review and, if needed, adjust the inferred data types so that key fields, such as customer IDs, are consistent instead of sometimes appearing as numbers and other times as strings. By treating the import step as a schema negotiation, you can align the stored metadata with your analytical needs and make later data cleaning more reliable. Python code, Parquet data imports. This section focuses on working with Parquet files using Pandas DataFrames. You will see how to import data from Parquet format and observe that it preserves the original schema and data types. After loading the data, you will also learn how to adjust column data types when needed so that downstream analysis remains accurate and reliable. We begin by importing the Pandas library to manage our data in a table-like structure called a data frame. We also import the datetime and time zone tools from the datetime module, so we can create timestamps that include time zone information. This setup allows us to work with time-based data accurately and consistently, which is essential for reliable analysis. We begin by building a dictionary called data that will serve as the basis for our data set. It has 3 entries that will become columns in a Pandas data frame. One for order identifiers, stored as strings, one for order amounts, stored as floating point numbers in US dollars, and one for purchase times, stored as date time objects, each datetime value is created with a specific year, month, day, hour, and minute, and all are set to the UTC time zone. Using a consistent time zone ensures accurate and comparable timestamps for any later time-based analysis, and this dictionary format makes it straightforward to convert the data into a data frame for further manipulation. We begin by creating a data frame from a dictionary that holds mixed data types, such as text, numeric values, and dates, and Pandas arranges this information into a table. After constructing the data frame, we display the data type of each column. This check is important because it confirms that Pandas has correctly recognized the types of data we provided. Verifying these types early helps ensure they match our expectations before we move on to any further processing or analysis. We first choose a file name, such as ordersexample.parquet, to define where the Parquet file will be saved in the current folder. Then we call the method that writes the data frame to this Parquet file. By setting the option to not include the index, we ensure that only the actual data columns are stored, keeping the saved file clean and focused on the relevant information. We load the Parquet file back into a new Pandas data frame to verify that the saved data and its schema are preserved correctly. Then, we print a short message to indicate that we are about to inspect the data types. Finally, we display the data type of each column in the loaded data frame so we can confirm that they match the original types before doing any further processing. Here we convert purchase timestamps from Coordinated Universal Time to the America-New York time zone. We take the column that stores the original UTC purchase times and use the Pandas time zone conversion method to shift them into local New York time. This step is important for analyses that depend on local context, such as aligning data with business hours or local events. The converted times are saved in a new column called Purchased at Local, so we keep both the original and the localized timestamps for further analysis. We keep the order identifier column as a string type in the data frame because even though the values may look like numbers, they are actually identifiers, not quantities. Treating them as strings prevents them from being used in unintended numerical calculations. It also avoids automatic formatting changes that might occur if they were interpreted as numeric values. This helps preserve the integrity and meaning of the identifier beta. The code first announces that it will display the adjusted data types of the data frame, so you can verify that recent transformations produced the expected types. It then prints the data types of each column in the adjusted data frame to confirm they are correctly set for further analysis. After that, it indicates that it will show a preview of the adjusted data. Finally, it displays the first few rows of the data frame so you can visually check that the transformations were applied correctly. This script shows how to work with Parquet files in Pandas while preserving data types. It creates a data frame with strings, floats, and time zone-aware timestamps, then saves it to a Parquet file and reads it back to confirm the types stay the same. It prints the updated data types and a sample of the data to demonstrate that Parquet maintains data integrity and that you can still adjust types after loading the file for accurate analysis. Troubleshooting data imports, encoding and missing values. When importing real-world datasets, You will often encounter text encoding problems and unexpected missing values. Encoding issues arise when the bytes in a text file are interpreted with the wrong character set, which can produce strange symbols or import errors. This is especially common with international data that includes non-English characters. It is important to recognize these symptoms as encoding mismatches, so you can fix the interpretation of the text, rather than assuming the data itself is corrupted. When dealing with encoding problems, start by considering where the data came from and how it was created. Modern web applications usually use UTF-8, while older systems may rely on Latin 1 or Windows-specific encodings. If characters and names look correct in a text editor, but appear wrong after import, or if you get decoding errors, it often means the declared encoding does not match the actual bytes in the file. By trying likely encodings based on the data source and checking the fields that look wrong, you can usually identify the correct encoding and restore the proper characters. Missing values can seriously distort your analysis if they are not handled correctly. Many datasets use placeholders, such as empty strings, dashes, or short codes like NA, to represent missing data, and these can be mistakenly treated as real values when the data is imported. If that happens, your statistics and visualizations may be misleading. To avoid this, you should examine the distribution of values and understand how the data was collected, so you can correctly mark these placeholders as missing without discarding genuine information. Python code, encoding and missing values. This section focuses on common problems that occur when importing data, such as encoding issues and incorrect placeholders for missing values. You will work with small CSV files that use different text encodings and special markers to represent missing data. By adjusting the encoding settings, you can fix garbled or unreadable text, and by specifying which values should be treated as missing, you can prevent placeholder symbols from being misread as real numbers. Together, these options help ensure that imported data is both readable and accurate. We begin by importing Pandas, a powerful tool for manipulating and analyzing data, which we will use to work with CSV files. We also import the input-output module, which lets us handle data streams and simulate file operations directly in memory. Together, these imports prepare our environment so we can read and process data efficiently without relying on physical files. We begin with a small CSV text that represents a simple dataset containing name, age, and height in inches. The names include accented characters, such as Jose and Mueller, which can create encoding challenges when importing the data. The age and height columns also use placeholder values like NA, 0, and -1 to stand in for missing information. This example is designed to show how both character encoding and placeholder values for missing data can affect the data import process. This code takes text that represents a CSV file and converts it into bytes using the Latin 1 encoding. This mimics how older systems might store the data. By encoding the CSV text in this way, it sets up a situation where character encoding problems can occur. This then allows us to later show how to correctly handle and fix those encoding issues. This example shows what happens when a CSV file encoded in Latin 1 is read as if it were UTF-8 using a data loading function. Because the encoding does not match, the program runs into decoding problems, especially with accented characters, which then appear garbled. The code wraps the read operation in a try-except block so that if a Unicode decode error occurs, it catches the exception and prints a message explaining that the import failed and includes the error details. Overall, it illustrates how using the wrong text encoding can break data import and how to handle that failure gracefully. We load the CSV data, which is stored as bytes, using the Latin 1 encoding, so that special characters like accented letters are read correctly. To do this, we use a byte stream that mimics a file and pass it to a Pandas data reading function. Specifying the Latin 1 encoding restores the proper characters in the names column. We then display the names to confirm they look correct, showing that the encoding problem has been fixed. We load the CSV data again, this time telling Pandas to use Latin 1 encoding, so special characters are read correctly. We also specify which entries should count as missing data by setting the missing values option to include the text NA, 0, and -1. This makes sure these placeholder values are treated as missing in the data frame. Finally, we display the data frame to verify that the missing values have been correctly identified and handled. This script shows how text encoding and placeholder values for missing data can affect importing data with Pandas. It creates a small dataset with accented characters and placeholders such as NA, 0, and -1, then encodes it using a legacy Latin 1 format. When the file is read as if it were UTF-8, the names become garbled, demonstrating what happens when the encoding is mismatched. Reading it again with the correct Latin 1 encoding restores the proper characters, emphasizing the need to match the file's encoding. The script also specifies which placeholder values should be treated as missing, allowing Pandas to convert them to proper missing value markers and handle them correctly during import. Fixin' mixed types. Mixed type columns can cause subtle problems when you import data because they mix values of different data types, such as numbers with text or dates. This often happens when numeric columns contain stray, non-numeric entries or when date columns use inconsistent formats. These mixed types can break operations like averaging, sorting, or date calculations. To avoid this, you should check column data types during import. Look for inconsistencies, and then clean and standardize the values so each column has a single, consistent type. When you suspect mixed data types in a dataset, first check the types assigned during import and see if they match what you expect. If a numeric column is treated as a generic type, some values are not being recognized as numbers, and if a date column is not stored as a datetime type, you may have inconsistent formats or invalid entries. This often happens in real datasets because of free text values or special markers like n/a or error. By reviewing a sample of values and comparing them with the dataset documentation, you can pinpoint which entries are causing problems with type detection. To fix mixed data types in a column, first decide what the correct type should be, then adjust the values to match it. For numeric fields, replace placeholders like NA or dashes with a consistent missing value marker. Then convert the column to a numeric type. For date fields, standardize the date formats and correct obvious errors before converting to a datetime type. If a column mixes fundamentally different kinds of content, such as numbers and comments, split it into separate columns. The overall goal is to keep each column in a single, appropriate data type that clearly reflects its purpose and handles exceptions in a deliberate way. Python code fixing mixed types. This lesson shows how to detect when imported data frame columns contain a mix of numeric values and non-numeric placeholders, and why that matters for analysis. You will see that these placeholders cause numeric operations to fail or give incorrect results. The lesson then demonstrates how to clean out the placeholders, convert the affected columns to proper numeric types, and run the same operations again. Finally, you compare the behavior before and after cleaning to understand the impact of mixed types on your analysis. We begin by importing the Pandas library, which lets us work with data structures, such as DataFrames, but are essential for handling tabular data. We also import the NumPy library, which supports efficient numerical operations. These two libraries are commonly used together for data manipulation and analysis. Setting them up at the start provides the core tools needed for the data cleaning and analysis steps that follow in the script. We create a data dictionary to hold example data with 3 fields: order ID, weight in pounds, and ship date. Each field is linked to a list of values, such as strings for order identifiers. The weight field includes strings that look like numbers, but also non-numeric placeholders like the word unknown or a dash. The ship date field contains date strings in different formats and placeholders like pending. This example illustrates how data imported from external sources can mix valid values with inconsistent or placeholder entries, which makes analysis more challenging. We begin by using the Pandas library to create a data frame from a data dictionary that includes columns with mixed data types. This new data frame is stored for later use. We then print a short message to indicate that what follows is the original data frame containing mixed types and display its contents. Seeing the data frame helps us confirm which columns have mixed data, setting the stage for cleaning or converting these columns later in the script. The code first announces that it will display the inferred data types of the data frame columns before any cleaning. It then prints the data type for each column. At this stage, some columns, such as weight in pounds and ship date, are classified as generic object types. This happens because they contain mixed values, like strings and numbers, so the library cannot yet convert them to more specific types, such as numeric or date and time. The code tries to compute the mean of the weight in pounds column, but this column contains mixed types, including strings, so the calculation is likely to fail. To handle this, the operation is wrapped in a try-except block. The try part announces that the mean calculation is starting and then attempts to compute it directly. If a type error occurs because of the non-numeric values, the except part catches it and prints a message explaining that the mean could not be calculated due to mixed types, along with the specific error message. We start by making a copy of the original data table so we can modify it without changing the source data. Then we focus on the column that stores weights in pounds, which currently mixes valid values with strings like unknown or a dash. We replace these placeholder strings with proper missing value markers using a special not a number value. This cleanup step is important because it allows us to safely convert the column to a numeric type and ensures that non-numeric entries are handled correctly. We convert the weight in pounds column to a numeric type using the Pandas to numeric function so that all values in the column are treated as numbers. This function tries to turn each entry into a number, and, with the errors set to coerce, any value that cannot be converted is replaced with a missing value. This step ensures the entire column is consistently numeric, which is necessary for performing accurate calculations and other numerical operations later on. We convert the ship date column to a proper date-time format using Pandas, so the dates can be handled consistently. By setting the errors option to coerce, any invalid or pending entries that cannot be converted are turned into a special missing value called not a time. This clearly marks problematic dates as missing instead of causing errors. Enabling automatic detection of the date format helps Pandas infer how the dates are written, which improves both performance and accuracy when parsing them. Next, we display the cleaned data table to verify that the cleaning steps worked correctly. This visual check confirms that placeholder values have been converted to proper missing entries and that each column now has the correct data type. By reviewing the printed table, we can be confident that the data is consistent and ready for further analysis or processing. We now print a message to indicate that we are about to display the data types of each column after cleaning and conversion. This lets us quickly verify that the types are consistent and suitable for analysis. We then show the data types of the cleaned table, confirming that the weight column is stored as a numeric value and the ship date column is recognized as a date. With these types correctly set, any future operations on these columns will work as expected. After cleaning the data, we can safely perform numeric operations on the columns. We then announce that we are calculating the mean shipped weight while ignoring any missing values. Next, we compute the average of the weight in pounds column in the cleaned data. This now works correctly because the column has been converted to a consistent numeric type, allowing the mean to be calculated without errors. This script shows how mixed data types in a Pandas data frame can break numeric analysis and how to fix them. It starts with numeric and date columns that contain non-numeric placeholders, so Pandas treats them as generic objects, and a simple task like computing the mean weight fails. The script then cleans the data by replacing placeholders with missing values, converting the weight column to a proper numeric type, and parsing the ship date column while turning invalid dates into missing values. After cleaning, the data frame has consistent types, and the mean weight can be calculated correctly, illustrating why data cleaning is essential for accurate analysis. Sampling imports with n rows. When working with large or messy datasets, avoid importing the entire file at once and instead start with a small sample of rows. This lets you quickly check whether columns are read correctly, headers are recognized, and there are no obvious problems like strange characters or wrong data types. By testing on a few hundred or thousand rows, you can adjust your import settings efficiently. Once everything looks correct, you can safely load the full dataset without wasting time or computing resources. When working with large datasets, it is important to first sample a small portion to check for irregularities. This quick inspection can reveal issues like inconsistent delimiters, mixed decimal separators, unexpected text in columns, or extra commas that shift data out of alignment. You might also find that some files begin with metadata instead of actual records, which means those lines need to be skipped. By catching these problems early, you can adjust your import settings and avoid repeatedly loading the full dataset during trial and error. When checking data with sampling, be aware that small samples can miss rare categories or unusual encodings that appear later in the file. Important issues, such as special characters in international records or uncommon codes in clinical data, may only show up after many rows. To reduce this risk, take samples from different parts of the dataset and compare the results for consistency. Once your checks work reliably across these varied samples, you can load the full dataset with greater confidence that many potential problems have already been addressed. Python code. Sampling imports with nrows. Use Pandas to demonstrate how to sample data during import by limiting the number of rows read from a large file. You can create a fake large CSV file, then load only a small number of rows using the option that restricts row count. After that, compare this sampled import with loading the full dataset to see how working with only a few rows might hide or reveal potential issues in the data. This helps you understand the trade-offs between quick sampling and complete data inspection when importing large files. We begin by importing Pandas, a powerful tool for organizing, manipulating, and analyzing data in a structured way. We also import the input-output module, which lets us work with data streams so we can treat a string as if it were a file. This combination allows us to simulate reading data from a comma-separated values file without needing an actual file stored on disk. Using these tools, we can conveniently load and process data directly from in-memory text. In this example, we create a multi-line text string that mimics the contents of a CSV file. Each row in the string has 4 fields: an identifier, a date, a temperature in Fahrenheit, and some notes. The data is intentionally designed to look like real-world input, including missing values, corrupted entries, and special characters. This setup will later be used to show how to read the string into a Pandas data frame and handle these common data quality issues. We use the string IO tool from the input-output module to create an in-memory text stream that behaves like a file. By passing our CSV text data into this stream, we can treat the string as if it were an actual CSV file. This allows libraries like Pandas to read the data directly from memory instead of from a file on disk. This approach is especially useful for testing or when the data does not need to be saved permanently. We use Pandas to read a CSV file from a buffer, but limit it to only the first 3 rows by setting the number of rows parameter to 3. This lets us quickly inspect a small sample of a large dataset without loading the entire file. By doing so, we save both time and memory while still getting an initial look at the data. The code prints a message explaining that it has sampled only the first 3 rows of the dataset, then displays those rows in a data frame. This provides a quick look at a small subset of the data. The main goal is to inspect or debug the data efficiently, without loading or viewing the entire dataset. The code moves the read position in the CSV buffer back to the beginning, so the data can be read again from the start. This is needed because the buffer was already read once to import a sample of the data. By resetting the position, the next read can access the entire contents of the buffer. This ensures that the full dataset is imported without skipping any information. The code loads the entire CSV file into a Pandas data frame by using the Pandas read CSV function on the CSV buffer. This operation reads all rows and columns into memory at once. As a result, you can access and analyze the complete dataset without any sampling or partial loading, which is useful when you need to work with all available data. The code first reports how many rows are in the full dataset by taking its length, giving a quick count of all entries loaded from the CSV file. It then reports the data type of the temperature column to show how the library interpreted those values. Knowing this data type is important for later processing or analysis, especially if the column might contain mixed types or missing values. This script shows how to use Pandas to read only a subset of rows from a CSV file by using the parameter that limits the number of rows. It first creates a simulated CSV file that includes missing values and corrupted entries, then reads just the first 3 rows into a data frame to quickly sample the data without loading the entire file. After that, it resets the data source and reads the full dataset to compare results. The output displays the 3-row sample, the total number of rows in the full dataset, and the data type of the temperature column, illustrating how incomplete or corrupted data can lead to data type inconsistencies. In this lecture, you learned to load tabular data from CSV, Excel, and Parquet files into Pandas 2.3.1 data frames using appropriate read_functions. Configure import options such as separators, headers, dtypes, and date parsing to correctly interpret raw files. And diagnose and fix common import issues, including bad encodings, unexpected missing values, and mixed type columns. In the next lecture, Lecture B, we will go over cleaning columns.
Thank you for your attention. See you all in the next lecture.